Assalamualaikum warahmatullahi wabarakatuh, and good morning to all of our viewers. My name is Fatima bin Hafiz, and today I'm going to be presenting the defect optimization of green part Ti-6AL-4V with pump steering binder using response surface methodology. So let's start with the introduction. What is metal injection molding? MIM. It is a manufacturing process that combines the technologies of powder metallurgy and plastic injection molding to produce complex metal parts with high precision and excellent mechanical properties. It is comprised of 4 parts, which is feedstock, injection molding, debinding, and also sintering. So there's 3 objectives of this research. First is to oversee the fabrication of Ti-6AL-4V using the metal injection molding, which is MIM, technique during the experiments with various process parameters. The second objective is to enhance the quality of the Ti-6AL-4V green part by optimizing for defects through the application of response surface methodology. Last but not least, the last objective of the day is to investigate and identify the best process parameters for producing defect-free green components in Ti-6AL and 4V. So now let's move on to the scope of study. So we have 3 scope of study, but now let's start with feedstock. So what is the scope of study for feedstock? It is the preparation of the feedstock by mixing the Ti-6AL-4V powders with pump stearin and polyethylene for their binders. So now let's move on to the next scope of study, which is injection molding. So the control of injection molding parameters such as injection pressure, injection temperature, power loading, mold temperature, and holding pressure to create green components. So the scope of study for the last one is defect analysis. So the defect analysis is detected by using design expert software. Now let's move on to the methodology. So for the methodology, let's start with the material. The material that is used in this research is Ti-6AL-4V metal powder, polyethylene, and also pump stearin. In the left hand side, we can see a small box that is showing the characteristic of the Ti-6AL-4V metal powder. Now for the next methodology, let us start with feedstock preparation. In this study, pump stearin is used as the main binder and polyethylene as the secondary binder. 3 different feedstocks were made with powder loadings of 63%, 65%, and 67%. The Ti-6AL-4V powder were mixed with 60% of pump stearin and 40% of polyethylene. This mixture was processed in a sigma blade at 150 Celsius for 1 hour. So for the next methodology is response surface methodology, or RSM. So what is RSM? RSM is a collection of mathematical and statistical techniques useful for developing, improving, and optimizing processes. So RSM often involves the use of design experiments to systematically collect data, example, factorial design FFD, central composite design CCD, and box backend designs BBD. So in the left hand side, we can see the injection parameter. This injection parameter is designed by the CCD, which is the central composite design. In the right hand side, we can see the small box that is showing the rating of defects, which include, for example, the weld lines, incomplete fillings, and also the separation of binders. Now let's move on to analysis of variance, which is ANOVA. ANOVA was used to analyze the regression equation and identify the interactions between the variables and the response. Then, the desirability function was used to determine the optimal levels of each independent variable to achieve the minimum defect rate of the green part. So on the right hand side, we can see that it is showing the equation of the defect rating, and then the optimized parameter, and the last one is the optimized defect of the green effect. So now let's move on to the results. So in the first slide, it is showing the results of ANOVA in the right hand side, and in the left hand side, we are showing the results of injection molding. So now let's move on to the next slide, which is the parameter interaction graph. So in the left hand side, there is a figure that is showing the interaction of injection pressure and also the mold temperature. While in the right hand side, we have a figure that is showing the interaction between the injection pressure and also the holding pressure. Both of these figures demonstrate how crucial it is to optimize injection pressure in order to ensure consistent mold filling, appropriate material flow, low internal stresses, and high quality products. A full and uniform filling of the mold cavity, sufficient packing to account for shrinkage of the material, reduced internal stresses and warping, superior surface smoothness, and dimensional correctness are all guaranteed by a properly balanced injection pressure. The ideal injection pressure must be carefully calibrated and monitored in order to produce products free of defects throughout the injection molding process. The interplay between injection pressure and mold temperature occurs to minimize the fall of the grain component. Next, let's move on to the third figure, which is the interaction of injection temperature and holding pressure. Holding pressure has a major effect on the quality of the result in injection molding. Faults can arise from both excessive and inadequate pressures. Because the material is pushed into the mold too forcefully, high holding pressure can cause flash, overpacking, higher residual stress, surface defects, and also longer cooling periods. Now let's start talking about the middle figure that is showing the interaction of injection temperature and power loading. Injection temperature is a critical parameter in injection molding, serving multiple essential functions in the process. It facilitates efficient material flow by ensuring the molten plastic reaches its optimal viscosity for filling intricate mold cavities accurately. Moreover, injection temperature plays a crucial role in maintaining the desired material properties, preventing premature degradation or overheating that could compromise the mechanical strength and structural integrity of the final product. Now, let's move on to the most right-hand side, which is the figure that's showing the interaction between the power loading and also the holding pressure. When referring to the concentration of solid particles combined with the binder to create a feedstock for injection molding, power loading is important since it influences the material qualities and features of the finished product. According to the figure that we've seen in the right hand side, different powder loading levels, for example 63%, 65% and 67% by weight affect the molded parts in various ways. At 63%, the feedstock has fewer solid particles, resulting in parts with lower density but potentially better flow properties. At 65%, there's a balance between density and flow, providing moderate mechanical strength and density, which is suitable for many applications. At 67%, the density and mechanical strength of the parts are higher, but the increased viscosity can make flow more difficult. In this slide, we can see this example of the defect. For example, we can see there's wet lines, slumping, and also flashing. So, in conclusion, the study successfully optimized defect ratings in grain component injection molding. Analysis with design expert software revealed that injection pressure had the greatest impact on defect rating. The optimized parameters were injection pressure 443.139 bar, injection temperature 142.11 Celsius, powder loading 65.35 volume percent, molding temperature for 44.684 Celsius, and holding pressure for 629.651 bar. These settings resulted in a defect rating of 2.5, with experimental value closely matching model predictions.